Table of symmetry in the factorial family. This section presents a numerical table that illustrates the symmetry and relationships among the factorial-type functions discussed earlier, including pi, gamma, delta, and their generalized or inverse forms. The variables a, b, and c are initially set to 1. Then d is defined as the sum of b and c. Similarly, e, f, g, and h are built by summing earlier values. H equals the sum of e, f, and g. The table then lists sequences of numbers in columns under these variables, showing how the sums progress in a symmetric, repeating pattern. For example, in the top rows, negative numbers appear, reflecting the behavior of the functions near negative or non-positive integers, which are the locations of poles for gamma and related functions. As you move down the table, the numbers increase, showing positive symmetry and the way these functions mirror each other around 0. The key idea is that these numbers encode the additive and multiplicative interconnections of the factorial family. The negative numbers correspond to poles or removable singularities. The positive numbers correspond to regular values or shifted factorial arguments. Overall, this table gives a visual representation of the intrinsic symmetry in the factorial family, highlighting how all the generalized, inverse, and periodic functions relate in a structured, predictable way. In simpler terms, you can think of it as a map of how these factorial functions mirror each other across different values, revealing hidden patterns in their relationships. Unification of the zeta series. This heading introduces the idea of bringing together various forms of the zeta series into a single, unified framework. The zeta series, which underlies the famous Riemann zeta function, involves infinite sums of numbers raised to powers and is deeply connected to prime numbers in complex analysis. By unification, the author is suggesting that all the different factorial-type functions, their inverses, and periodic or generalized versions can be systematically related to the zeta series. This sets the stage for showing how all these functions, which might seem different at first, actually follow a common pattern or functional structure. In simple terms, think of it as lining up all these different series and factorial-related functions so you can see a single, coherent mathematical pattern behind them. Chapter 3. Executing the proof. The chapter begins by introducing lemmas related to factorials. Lemmas are small, supporting results or stepping stones that help in proving a bigger statement. In this case, the Riemann hypothesis. The author plans to explore some new mathematical insights about factorials that will be useful for the proof. 1.1 Recalling gamma and pi functions. To start, the text reminds us of the gamma function, which generalizes the factorial function. Historically, Euler in 1730 showed that the factorial of a number x, which is the product of all positive integers up to x, can be represented by an integral for any real number greater than 1. Specifically, the factorial of x, written as x factorial or x, is equal to the gamma function of x, which is the integral from 0 to infinity of t raised to the x minus 1 times the exponential of minus t, integrated with respect to t. In simpler terms, instead of multiplying numbers directly, we can use this continuous formula involving an integral to compute factorials for not just integers, but all positive real numbers. This section sets up the foundation by recalling the gamma function, which is essential because many of the factorial-related lemmas and functional relationships used in the proof rely on this concept. 1. Lemmas related to factorials. First, the text recalls Euler's pi function, which satisfies a simple recurrence relation for all positive real numbers. If you take x plus 1, the pi function at that point equals x plus 1 times the pi function at x. In other words, each step builds on the previous value, just like factorials. In 1768, Euler introduced the gamma function. This function extends the concept of factorials beyond positive integers to all real numbers, including negative numbers except 0 and negative integers, where the function is not defined. The gamma function can be thought of as a shifted version of the pi function. Specifically, the gamma function of x is defined as the integral from 0 to infinity of t raised to the x minus 1 times the exponential of minus t, integrated with respect to t. There is a direct relationship between the gamma function and the pi function. The gamma function at x plus 1 equals the pi function at x plus 1, which also equals x factorial. So, for example, gamma of 4 equals 3 factorial, which is 6. The gamma function has several important properties. It is defined for complex numbers z with positive real part as the integral of t to the z minus 1 times e to the minus t. It is analytic, meaning smooth and differentiable, everywhere in the complex plane except at 0 and negative integers. At non-positive integers, it has a simple pole, and the residue at z equal to a non-negative integer n is given by alternating signs and n factorial. It satisfies a recurrence relation, gamma of z plus 1 equals z times gamma of z. For positive integers, the gamma function simply reproduces the factorial gamma of x equals x minus 1 factorial. This section sets the stage for later lemmas by summarizing Euler's pi function, the gamma function, and their key properties, which are fundamental tools for exploring factorial relationships in the Riemann hypothesis. 1.2 Introduction of the delta function. The text now extends the idea of factorials to include negative integers by shifting the argument of the gamma function even further down by 1 unit. The author introduces a new function called the delta function, which should not be confused with the small delta used in Dirac's delta function in physics. The delta function is defined as an integral from 0 to infinity. You take t raised to the x squared power, multiply by the exponential of minus t, and integrate with respect to t. This is similar in form to the gamma function, but with a squared exponent. The author explains the choice of the name delta. It's not personal. It's chosen because in the Greek alphabet epsilon sits between pi and gamma, forming a semicircle. The delta comes next, completing the cycle. This is meant to reflect the pattern 1 plus something, or 1 plus something squared, or something minus 1, something squared minus 1. So the name delta symbolizes this continuation of the factorial family in a cyclic, almost geometric sense. Then, for complex numbers with positive real parts, the author uses integration by parts to express delta of z plus 2 as the integral from 0 to infinity of t to the z plus 1 times e to the minus t. In short, the delta function is a natural extension of the gamma function designed to handle factorial-like operations for negative numbers and powers, keeping a kind of cyclic harmony in the factorial family. This part is about deriving a recurrence relation for the delta function, similar to what we have for the gamma function. We start with delta of z plus 2, which is the integral from 0 to infinity of t raised to the z plus 1 times the exponential of minus t. To simplify it, we use integration by parts. This is a standard technique where we split the integral into two parts, an algebraic part and an exponential part. Here, the algebraic part is t to the z plus 1, and the exponential part is e to the minus t. After applying integration by parts, the integral separates into a boundary term evaluated at 0 and infinity, plus another integral. The boundary term vanishes because when t is 0 or infinity, the expression t to the z plus 1 times e to the minus t goes to 0. What remains is z plus 1 times an integral that looks almost like the original delta function, but with the exponent reduced by 1. Repeating this integration by parts one more time reduces it further, giving z plus 1 times z times the integral from 0 to infinity of t to the z minus 1 times e to the minus t, which is exactly delta of z. So, the recurrence relation emerges clearly when delta of z plus 2 equals z plus 1 times z times delta of z. In simple terms, this is exactly like the factorial pattern. N factorial times n plus 1 gives n plus 1 factorial, but now extended to this more general delta function. It shows how the delta function naturally multiplies by successive terms when we shift its argument. This section is about the properties of the delta function and how it connects to the gamma and pi functions. Just like the gamma function, the delta function is defined as an integral from 0 to infinity with t raised to a power times the exponential of minus t. For the delta function, that power is 2 less than the argument, so we have t to the z squared times e to the minus t. The delta function is analytic, meaning it behaves smoothly everywhere except at certain points, which are positive integers starting from 1. At these points, it has simple poles, and the residue at each pole is exactly 1 over n factorial with an alternating sign pattern, like the gamma function. The delta function also satisfies a recurrence relation, If you increase its argument by 1, it multiplies by the current argument. Increasing by 2 gives a product of two successive terms, exactly like factorials. For integers, delta of x plus 2 equals x plus 2 times x plus 1 times delta of x, which mirrors the factorial pattern. Importantly, this delta function helps remove the poles of the gamma and pi functions. In other words, by using delta, we can rewrite expressions like gamma of x plus 1 or pi of x in a way that avoids the singularities, the points where these functions blow up. For simplicity, examples are often given for integers, but the same rules extend to fractions, complex numbers, and other values within an extended domain. In short, the delta function extends the factorial concept further, gives a clean recurrence relation, and provides a tool to handle the singular points of gamma and pi functions. This section explores how the extended factorial functions gamma, pi, and delta interact and form a kind of harmonic structure. The author starts by plugging in small integer values into these functions to see how they behave. For example, when the input is 2, the sequence gives values like 4 becomes 3, 3 becomes 2, and so on, eventually giving 2. When the input is 1, the result comes out as 1. When the input is 0, the result is still 1. These calculations show that the three factorial functions gamma, pi, and delta are behaving together like a triangle of a harmonic trio. Here, gamma is considered the central function, while pi and delta act as its harmonic partners. The idea of harmonicity comes from complex analysis. If a function is analytic, its real and imaginary parts are harmonic functions. The text connects this to the zeta function, which also has harmonic components. Essentially, because the delta function is defined carefully, the zeta function harmonizes these factorial functions, meaning their behaviors align in a smooth, structured way. Specifically, the real and imaginary parts of the reciprocal function 1 over z are harmonic except at the origin. Since the factorial type functions are defined via integrals that build on 1 over z, the integrals inherit this harmonic property, reinforcing the connection between gamma, pi, and delta. In simpler terms, gamma, pi, and delta are not just independent extensions of factorials, they interact in a structured, harmonic way, which is crucial for understanding the deeper properties of the zeta function and, ultimately, the Riemann hypothesis. This establishes a foundation for seeing these factorial functions as part of a coherent, interconnected harmonic system in complex analysis. This section continues building the harmonic picture of the factorial functions gamma, pi, and delta within complex analysis. The author begins by noting that since these functions are continuous and the complex plane can be viewed as a complete and finite circle, we can safely interchange the order of integration when working with linear combinations of these functions. This is a technical way of saying the manipulations are mathematically sound. Next, the author introduces two additional harmonic functions centered around delta. This is done to unify the symmetries of 5 factorial type functions, the original 3 gamma, pi, delta plus these two new harmonic companions, creating a fully symmetrical, interconnected system. Then, the author demonstrates how to remove poles of the gamma and pi functions by evaluating the integrals at specific integer values. For input equal to 1, the integrals reduce to simple finite values, ultimately giving 1. This shows that potential singularities, poles, at these points can be neutralized using the integral representation of the functions. Similarly, for input equal to 2, the integral calculations again remove poles and produce consistent finite results. In essence, by carefully choosing these integral representations and evaluating at certain integer points, the author shows that gamma and pi can be extended without singularities, maintaining harmonicity and symmetry with delta and the other introduced functions. The takeaway is that all 5 factorial type functions can be harmonized in a continuous, symmetrical framework, laying the groundwork for further developments in the proof of the Riemann hypothesis. In short, the functions are carefully aligned so that any singular behavior is cancelled, and all functions behave together in a smooth, harmonic, and symmetrical way. This section continues the process of removing poles and establishing harmonic relationships among the factorial type functions gamma, pi, and delta using concrete integer examples. The author begins by evaluating the integral representations at small integer inputs, starting from 0. At these points, the integrals simplify nicely, giving consistent finite results, usually 1, which demonstrates the functions are well behaved at these points. Then, the process is continued for higher integers. For input 3, the evaluation shows that the values align with previous results, producing a finite number like 2. For input 4, the results correspond to 3, and similarly for 5 and 6, producing factorial-like sequences such as 1/6, 1/24, and 1/120th. What is happening here is essentially the reproduction of factorial values using these extended integral definitions, while at the same time removing any singularities that would normally appear in the gamma or pi functions at negative or 0 points. Each step is like building a harmonic ladder, where each integer input produces a consistent output, maintaining symmetry and continuity across the factorial family of functions. In simpler terms, by carefully evaluating these integrals at successive integers, the author shows that gamma, pi, and delta can be harmonized and extended safely, producing the familiar factorial sequence without running into infinities or undefined values. This forms a key step in establishing the structural harmony among these functions, which is important for the larger proof strategy. This section continues the step-by-step evaluation of factorial-related functions gamma, pi, and delta using integer inputs, extending the pattern we saw earlier. At each integer input, the author plugs in the value and computes the integral representations. For instance, at input 7, the functions evaluated at 5, 6, and 7 produce the results 6 and 1/120. Moving to higher integers, we see the same factorial pattern emerging. Input 8 gives results corresponding to 7 and 1/720. Input 9 gives 8 and 1/5040. Input 10 gives 9 and 1/40,320. Input 11 gives 10 and 1/362,880. Essentially, what is happening is that the factorial values are being reconstructed step by step from these integral definitions, and each function's evaluation is consistent with the previous step, showing a smooth, continuous extension of factorials. This process removes any poles or singularities that might appear in the standard gamma or pi functions at lower or problematic points. In simple terms, the author is building a harmonic ladder of factorial values, confirming that these extended functions reproduce the familiar factorial numbers while maintaining continuity and symmetry. This systematic evaluation is key to harmonizing the gamma, pi, and delta functions, which is foundational for the larger proof strategy related to the Riemann hypothesis. The text continues the step-by-step evaluation of factorial-related functions for higher integers. When we plug in 12, the functions evaluated at 10, 11, and 12 give 11 and 1/36,280,000. Plugging in 11, we get the next factorial, 12 and 1/39,916,800. The author notes that this pattern continues indefinitely, extending in principle toward negative infinity as well, showing the continuity and consistency of these extended factorial definitions. Next, the author introduces a connection between the delta function and the Riemann zeta function, starting with the delta function defined as an integral involving the variable t squared. They perform a substitution of t with n times u, effectively scaling the variable. After substituting, the integral transforms so that powers of n appear outside the integral and the remaining integral is expressed in terms of u. The resulting expression shows that the delta function can be factorized in terms of powers of n and an integral over u, which sets up a direct relation between the delta function and the zeta function, since the zeta function involves sums over powers of integers. In simple terms, this step bridges the delta function to the zeta series, showing how these factorial-like integrals connect to sums over integer powers, which is central for later steps in proving the Riemann hypothesis. Essentially, this section is building the tools to link extended factorial functions with the structure of the zeta function, laying the groundwork for harmonic and analytic relationships used in the proof. The text continues developing the link between the delta function, factorial functions, and the zeta function. First, the delta function is expressed as a sum over all positive integers. Specifically, The author writes it as a sum of terms where each integer n is scaled by n raised to the x power. By substituting and rearranging the order of summation and integration, the integral over u appears inside the sum. This shows that the delta function can be represented as an infinite sum of integrals, each associated with a different integer n. The author then manipulates the sum to show that it can be rewritten in terms of the standard zeta function, because the sum over 1 divided by n to the x naturally appears. In other words, the integral expression for the delta function encodes the same information as the zeta series, making the connection explicit. After some further manipulations, the expression is simplified into a form that separates the exponential term from the integral, preparing it for harmonic analysis. Next, the text introduces the concept of a periodic harmonic conjugate of the gamma function. Lemma 4 defines a periodic gamma function as a harmonic conjugate of the capital gamma function. In simpler terms, this means we can construct a new function that shares a harmonic relationship with the gamma function, much like sine and cosine are harmonic conjugates. This new periodic gamma function is expressed as an integral very similar to the original gamma function, but shifted to reflect the harmonic repeating behavior needed for analysis on the unit circle. So, the key ideas are: the delta function can be rewritten as a sum over integers, directly relating it to the zeta function. A periodic harmonic version of the gamma function is introduced, which will play a role in understanding the deeper analytic and harmonic properties of these functions. This sets up the tools for connecting factorial-like integrals to the zeta series while respecting the harmonic structure in the complex plane. The text now focuses on the periodic gamma function, denoted as pz, and explores its properties, similar to the standard gamma function but with harmonic or periodic adjustments. First, consider a complex number z with a negative real part. The author applies integration by parts to the integral defining the periodic gamma function. Through this process, the integral is broken into a boundary term and another integral. The boundary term vanishes, and what remains is the integral of t raised to z minus 1 times the exponential of t. This simplifies to z times the standard gamma function evaluated at z, which is equivalent to the gamma function at z plus 1. In simple terms, this shows a recurrence property. The periodic gamma function at z plus 1 equals z times the periodic gamma function at z, just like the classical gamma function. Next, the text lists the key properties of this periodic gamma function. It can be expressed as an integral over positive t, similar to the gamma function, but with the exponent adjusted to reflect periodicity. It is analytic everywhere in the complex plane except at the non-negative integers, where it has singularities. At each non-negative integer z equals n, it has a simple pole, and the residue at that pole is 1 divided by n factorial, matching the structure of the classical gamma function. It satisfies the recurrence relation, meaning the function at z plus 1 equals z times the function at z, which is fundamental for all gamma-type functions. So essentially, the periodic gamma function behaves very much like the classical gamma function, but it is framed in a periodic harmonic context, making it suitable for applications where periodicity and harmonic conjugates are important, such as in the study of zeta and related functions. The text now extends the ideas of periodicity and harmonic conjugates to the delta function, similar to what was done with the gamma function. First, the periodic gamma function is highlighted again. It satisfies the recurrence relation, which means that if you evaluate it at x plus 1, you get x times the function at x. This mirrors the classical recurrence property of the gamma function. Then, the author introduces the periodic delta function, denoted as px, which is constructed as the harmonic conjugate of the capital delta function. In other words, it is a version of the delta function adjusted to respect periodicity and harmonic relationships in the complex plane. Its defining integral is over positive t, with t raised to x plus 2 times the exponential of t. This parallels the way the periodic gamma function is defined, but shifted appropriately to match the delta function's structure. So, just like the periodic gamma function captures harmonic and periodic behavior while preserving recurrence, the periodic delta function does the same for the delta function, preparing it for use in more advanced constructions like zeta function harmonization and pole removal. The text is now analyzing the periodic delta function more closely, using techniques similar to those for the gamma function. We start with the periodic delta function evaluated at z plus 2, where z is a complex number less than 0. Using integration by parts, the integral can be rewritten step by step, and the boundary terms vanish. This leads to the recurrence relation that p of z plus 2 equals z plus 1 times p of z plus 1, which in turn equals z plus 1 times z plus 1, or simply z plus 2. Essentially, this shows that the periodic delta function satisfies a recurrence property just like the standard delta and gamma functions, but shifted appropriately to match the structure of delta. The properties of the periodic delta function are summarized as follows. It is defined by an integral over t raised to z plus 1 times the exponential of t. It is analytic on the complex plane except at positive integers starting from 2. It has simple poles at positive integers, with residues following the factorial pattern of 1 to the power n over n factorial. It satisfies the recurrence relation p of z plus 1 equals z times p of z for all relevant z. In short, the periodic delta function behaves harmonically and periodically, preserves recurrence, and has well-defined poles and residues, making it a natural counterpart to the standard delta function in the extended complex domain. This section introduces the idea of a closure of the factorial operation using what the author calls the 5 factorial functions. These 5 functions include the classical gamma function, the pi function, the delta function, and their periodic counterparts. The periodic delta function satisfies a recurrence relation, meaning that its value at x plus 2 can be expressed as x times its value at x plus 1. The author then shows that all 5 factorial functions are interconnected in a consistent way. For positive numbers, the value of x plus 2 in any of these 5 functions can be expressed recursively in terms of x plus 1 and x, linking all 5 together. For negative numbers, the same kind of relationship holds with the inverses of the 5 factorial functions following the similar pattern. This ensures that factorials are well defined and consistent even for negative arguments using these extended functions. Lemma 6 formalizes this idea. The 5 factorial functions provide a closure for factorials, meaning that starting from the gamma function as the central function, all other factorial values positive, negative, or 0 can be computed consistently. The text gives concrete examples. For 0, 1, and 2, the values of the 5 factorial functions align with the expected factorials. For instance, 0 factorial equals 1, 1 factorial equals 1, and 2 factorial equals 2. Similarly, the periodic functions also align, ensuring complete harmony among these functions. In essence, this framework guarantees that factorials behave consistently across all these related functions, forming a harmonious and closed system centered around the gamma function. This section continues demonstrating how the 5 factorial functions, the gamma function, pi function, delta function, and their periodic versions align perfectly with the classical factorials for positive integers. The author plugs in specific integer values into these functions to show their values match the expected factorial results. For example, when we look at 2, the values of the inverse functions and the periodic functions all yield 2 factorial, which is 2. Moving on, for 3, all 5 functions give 3 factorial, which is 6. Similarly, for 4, all 5 functions produce 4 factorial, which is 24. This pattern continues consistently for higher numbers. 5 gives 126, gives 727, gives 5,048, gives 40,329, gives 360, 2,880. The key idea here is that these extended factorial functions not only generalize factorials to non-integers or negative numbers, but also reproduce the classical factorial values exactly for positive integers. In other words, the gamma, pi, delta, and their periodic versions form a harmonious, unified system that is fully consistent with ordinary factorials, establishing a foundation for further analytic work like in the proof of the Riemann hypothesis. This step-by-step matching shows that the system of 5 factorial functions is robust and reliable, behaving exactly as expected for all integers tested. The text first continues the pattern of the factorial functions for positive integers. For example, when we plug in 10, 11, and 12, all 5 factorial functions, gamma, pi, delta, and their periodic versions give exactly the classical factorial values. For instance, 12 factorial equals 3,628,800. The author notes that this pattern of exact agreement continues all the way down to negative infinity in the extended domain of these functions. This demonstrates the robustness and consistency of the five-function system across all integers. Next, the text moves to lemmas related to the zeta function, which are important for advancing toward the proof of the Riemann hypothesis. The author introduces a harmonic zeta function and an alternate form of its functional equation. Starting from Riemann's functional equation, they multiply both the numerator and denominator by a shifted factorial term. This produces an expression where the shifted factorial term interacts with the zeta function, and by using the property that the product of two shifted factorials equals a factorial at a combined argument, the equation simplifies nicely. In essence, this section shows how the factorial functions and the zeta function are interconnected and sets up a framework for manipulating the zeta function in a way that will be useful in proving the Riemann hypothesis. It highlights the harmony between factorial-based functions and zeta function identities, which is a central theme in Surrogate Gauch's approach. This section develops lemmas about the zeta function that help in manipulating it for the proof. The author starts with an assumption about limits. When you take the limit as s approaches 1, the product of a shifted factorial term and the zeta function approaches 1. In simpler terms, this gives a kind of normalization condition for the zeta function. Using this, they write an equation for the zeta function where it is expressed as a fraction. The numerator involves a signed term and a power of 2, and the denominator involves shifted factorials. Next, they multiply both numerator and denominator by additional factorial terms. This is a standard trick in algebra. Multiplying top and bottom by the same thing doesn't change the value, but it allows the expression to be reorganized in a useful way by using properties of these factorial terms, specifically that the product of some shifted factorials simplifies into a single factorial at a combined argument. They rewrite the zeta function in a cleaner form. The process is repeated with another multiplication, showing how the zeta function can be systematically expressed in terms of these factorial functions. Finally, they restate the assumption about the limit at the end to reinforce that this normalization is a key part of the setup. In essence, this passage is showing how the zeta function can be rewritten using the factorial family, which sets the stage for deeper manipulations in the proof of the Riemann hypothesis. It emphasizes the interplay between the zeta function and the extended factorial functions. This section continues the process of rewriting the zeta function using factorial terms. It starts with an equation expressing 1 as a fraction. The numerator involves a signed term and a power of 2, and the denominator involves shifted factorials. Next, the author multiplies both sides by another factorial term, in this case the one corresponding to 2 times s. This doesn't change the equality, but it allows the expression to be reorganized. After this step, the zeta function expression now involves a new factorial in the denominator. Then, they multiply by yet another shifted factorial corresponding to s minus 1. This introduces additional factorial terms into the expression, gradually building up a chain of factorials that relate to each other. They introduce a second assumption about limits. When s2 approaches a certain value, the product of this new factorial term and the previous one approaches 1. This again acts as a normalization condition, similar to the first assumption. Using this assumption, the fraction simplifies. The product of these factorial terms cancels in a way that leaves a clean expression, showing that the zeta function can be expressed in a factorial-based fraction form, with one of the factorials now appearing separately on the side. In short, this passage shows a systematic way to expand and simplify the zeta function using shifted factorials and limits, which sets up the structure needed for the later parts of the proof. It's all about managing factorial products to represent the zeta function cleanly. This section discusses how the zeta function behaves around its pole at s equals 1. The equation being considered is consistent with the analytic continuation of Riemann's functional equation. That means the formula works not just for the original domain of the zeta function, but also in a larger complex plane. The author points out a harmonic conjugate relationship This is a way of saying that the zeta function has paired real and imaginary parts that interact smoothly around the pole, much like waves that are in harmony. This perspective leads to thinking about a multi-zeta function viewpoint, meaning we can consider several interconnected zeta-type functions simultaneously, each related by these factorial-like shifts. By setting one of the shifted factorial terms equal to 1, the equation simplifies, showing a clear relationship between the signed term, powers of 2, and the remaining factorials. This simplified form matches Riemann's original functional equation, confirming that the manipulations are consistent. Lemma 7 then shows different equivalent forms of the zeta function using different factorial related functions. One version uses a shifted factorial corresponding to 4 times s, another uses the gamma function form with 3 times s, and yet another uses the pi function with 2 times s. In essence, this passage shows that the zeta function can be expressed in multiple but equivalent ways using shifted factorials, gamma, or pi functions, and these forms all preserve the core behavior that leads to its zeros. This section moves from factorials and zeta functions to logarithms and geometry, especially the unit circle. First, the author notes that using Euler's induction approach, the zeta function can be defined to take the value 1 for certain points, called S sub n. This is consistent with all the rules of complex analysis, meaning the zeta function can be viewed in multiple overlapping ways, a multi-zeta perspective. Next, the text revisits the unit circle, which is a circle centered at the origin with a radius of 1. This is a foundational tool in both trigonometry and complex analysis. Each point on the unit circle corresponds to an angle, and the coordinates of that point give the sine and cosine values for that angle. If we look at every 30-degree angle, the sine squared plus cosine squared always equals 1. This creates a repeating pattern fit every 330-degree steps. We have a kind of minicycle, and 6 repetitions of these minicycles complete a semicircle. 2 semicircles, or 12 of these minicycles, complete the full circle. Essentially, this sets up a way to think about periodicity and symmetry, which will later be useful in understanding the harmonic properties of logarithms and zeta-related functions. In simple terms, the unit circle's structure is being used to understand cycles, repetition, and harmony in the complex plane, which connects to the behavior of zeta and logarithm functions. This section explores negative logarithms and their connection to the unit circle in complex analysis. In the complex plane, every complex number can be represented in polar form using a distance from the origin and an angle, called the argument or phase. The angle corresponds to a point on the unit circle, which shows the direction of the complex number. Euler's formula links exponentials and trigonometry, stating that raising e to an imaginary angle equals the cosine of the angle plus I times the sine of the angle. This shows a deep connection between circular motion and complex numbers. But the unit circle is not just about trigonometry. Arithmetic operations like addition, subtraction, multiplication, and division also have cyclic patterns. For example, adding or multiplying repeatedly eventually relates back to 0 or 1, creating a cycle of 3 steps in certain cases. These cycles extend to nonlinear functions too, like polynomials, exponentials, and logarithms. Logarithms of negative numbers do not exist in ordinary real numbers, but in the complex numbers, they can be defined using Euler's formula. The complex logarithm is multivalued, meaning it can take multiple values that differ by integer multiples of 2 times I. To make it single-valued, mathematicians choose a principal branch, often cutting along the negative real axis. To fully define the complex logarithm and complete the cycle, we need a specific real choice for the imaginary unit I, giving it a unique lowest value. This allows us to theoretically reach all real numbers through the complex logarithm. In short, the unit circle helps us understand how complex exponentials, negative logarithms, and cyclic behavior all fit together, showing a harmony between arithmetic, algebra, and complex analysis. This section continues the discussion of complex numbers, the unit circle, and logarithms. The text lists angles from 0 degrees up to 360 degrees in increments of 30 degrees. Each of these angles corresponds to a point on the unit circle, which helps visualize how complex numbers rotate around the origin. There are expressions like the exponential of the natural logarithm of a fraction, for example, e to the power of the natural log of 3 halves, or e to the power of the natural log of 1/2. These are ways of expressing numbers in exponential form, often used to simplify powers and logarithms. Then it introduces Euler's formula, which states that a complex number can be written as a distance from the origin times the cosine of the angle plus I times the sine of the angle. Symbolically, a complex number z equals r times cosine of x plus I times sine of x, where r is the magnitude and x is the angle. Using Euler's formula, e raised to I times an angle equals the cosine of that angle plus I times the sine of that angle. This connects trigonometric form and exponential form of complex numbers, allowing rotation and scaling to be expressed neatly. The examples like e to the I times 3 halves or e to the I times 1/2 are just particular points on the unit circle represented in exponential form. In short, this passage shows how angles, trigonometry, and exponentials all work together to represent complex numbers on the unit circle, and it sets the stage for using these ideas in understanding logarithms, negative numbers, and cycles in complex analysis. This section explores complex numbers, the unit circle, and something called the negative logarithm, using ideas from trigonometry and Euler's formula. First, any complex number can be written in exponential form as a distance from the origin times e to the I times an angle. For example, z equals e to the I times x. If we set x to I itself, Euler's formula gives e to the I times I equals 1. If x is 1/2, then e to the I times 1/2 equals I. These are examples of how different angles or inputs produce specific points on the unit circle. The unit circle is defined by all complex numbers whose magnitude or distance from the origin is 1. So the magnitude of z, written as the absolute value of z, is 1. The text points out that the imaginary unit I is not yet fully defined numerically, but using the trigonometric form, for instance with x equals 3 halves, the point z on the circle is cosine of 3 halves plus I times sine of 3 halves. Calculating its magnitude confirms that it still lies on the unit circle. Then the text introduces a new variation called the d-unit circle, represented by 1/2 times e to the I times x equals 1. This equation creates a kind of mathematical duality, splitting a singularity into two perspectives. This is particularly useful when studying prime numbers and the zeta function. Visually, you can think of the unit circle being projected onto a unit sphere. Points inside the circle map to the southern hemisphere, points on the circle map to the equator, points outside the circle map to the northern hemisphere. The d-unit circle behaves similarly, creating parallel disks on this sphere corresponding to different magnitudes. Together, the regular unit circle and the d-unit circle form a complete algebraic cycle. Finally, by treating I as a constant scale factor, we can visualize the imaginary axis as maintaining the rotational symmetry of this trigonometric cycle of 3. The imaginary values reflect along the real axis, and this cycling behavior continues alternately, creating a dynamic, harmonic structure. In essence, this section links unit circles, complex exponentials, and projections onto spheres to give a geometric and algebraic picture that supports the deeper study of the zeta function and prime numbers. This section is about complex numbers, unit circles, and their geometric projections, connecting them to ideas like lattice points and placeholders in number systems. First, the author mentions lattice points 1, I, -1, I, and 0. These are key points on the complex plane that act like mid-values or balance points. For example, if you take the combination of 1 plus I minus 1 minus I, you get 0. This shows a kind of symmetry or balance among these points. The text connects this to the decimal number system. The concept of placeholder zeros is essentially a way of completing or balancing the complex unit circle. It's a way to represent numbers fully, ensuring the cycle is complete. Next, the unit circle in the complex plane is projected onto the unit sphere using stereographic projection. Here's how it works. Points inside the unit circle map to the southern hemisphere of the sphere. Points on the unit circle map to the equatorial plane. Points outside the unit circle map to the northern hemisphere. Similarly, the d-unit circle, a modified version of the unit circle introduced earlier, can be projected onto a d-unit sphere. This projection reveals 3 parallel disks. These disks represent 3 equivalent unit values in different senses, one in the southern hemisphere, one on the equator, and one in the northern hemisphere. Finally, the polar sphere handles points that lie outside the d-unit circle, completing the geometric picture. In short, this passage shows how complex numbers and their unit circles can be visualized in 3 dimensions using spheres. The d-unit circle adds another layer, revealing hidden structure and symmetry among numbers and linking complex analysis to geometric intuition. This section is about visualizing the complex plane, the unit circle, and the zeta function in 3 dimensions, particularly in relation to the critical line of zeta zeros. The author talks about an axis of rotation, which you can imagine as the vertical line around which these surfaces are spun or projected. The unit surface corresponds to the regular unit circle projected into 3 dimensions. It is assigned a value of 1. The d-unit surface, which comes from the earlier concept of the d-unit circle, is slightly larger and is assigned a value of 2. The North Pole represents infinity, while the South Pole corresponds to 0. This sets up a scale from 0 at the bottom to infinity at the top. Between these extremes, there is a half-unit surface with a value of 1/2. The text describes 3 parallel surfaces within a single cone, which you can picture as 3 horizontal slices inside a cone. Each slice represents a different magnitude, like one for the half-unit, one for the unit, and one for the d-unit, giving a unified, absolute view of the complex structure. In short, this is a geometric model that visualizes the critical line of the zeta zeros and related structures in terms of stacked surfaces, helping to understand the hierarchical and symmetrical relationships among numbers in the complex plane. This section is about examining the equation where the magnitude of a complex number z, written as half times e to the ix, is claimed to equal 1. The author wants to show that this is impossible. Let's break it down. Complex number z, when we write z in polar form as r times e to the I times theta, where r is the magnitude of z and theta is the angle. Magnitude of z, when the magnitude or length of z is always a non-negative real number. We denote this as the absolute value of z, which equals r. Exponential form, from the expression 1/2 times e to the ix, represents a complex number whose magnitude is exactly 1/2 and whose angle is x. The equation under consideration from the claim is that the magnitude of z equals this number and is also equal to 1. In symbols, this says that the magnitude of z, which is 1/2, equals 1. Magnitude comparison pulling. But the magnitude of a complex number is always a real, non-negative number, and clearly 1/2 does not equal 1. So, the conclusion is that this equation cannot be true. The magnitude of z cannot simultaneously be 1/2 and 1, showing the impossibility of the claim. This sets the stage for understanding constraints on complex numbers and their representations, particularly when exploring the geometry of the zeta function and unit circles. The author is examining the magnitude of the complex number 1/2 times e to the ix. First, the magnitude of 1/2 times e to the ix is calculated. Since the magnitude of e to the ix is always 1, multiplying it by 1/2 gives a magnitude of exactly 1/2. So, the magnitude of 1/2 times e to the ix is 1/2. Now, the equation under consideration claims that this number equals 1. To check this, we compare magnitudes. For a complex number equation to be true, the magnitudes on both sides must be equal, but the magnitude of 1/2 times e to the ix is 1/2, which is clearly not equal to 1. Therefore, the equation 1/2 times e to the ix equals 1 cannot hold because the magnitudes are not the same. This reinforces the impossibility discussed earlier. A complex number with magnitude 1/2 can never be equal to a number with magnitude 1. The author is continuing to examine the equation 1/2 times e to the ix equals 1 and why it cannot be true. First, he points out the obvious. The magnitude of 1/2 is not equal to 1, so the statement 1/2 equals 1 is clearly false. This immediately shows that the equation 1/2 times e to the ix equals 1 cannot hold because the sizes or magnitudes do not match. Next, the author introduces a special assumption. He temporarily treats I, which is normally the imaginary unit, as the natural logarithm of 2, a real number. This is an unusual assumption, but it's used here to test the equation in a different way. Then he writes the complex number in exponential form 1/2 times e to the ix, where x is the angle or argument. Finally, He begins analyzing what happens under this assumption to see if the equation could somehow hold, even though we already know the magnitudes contradict. This sets up a formal contradiction analysis. In short, the key idea is, under normal complex analysis, the equation is impossible because the magnitude 1/2 is not equal to 1, and even with this unusual assumption about I, the equation will lead to a contradiction. The author is continuing the analysis of the equation 1/2 times e to the ix equals 1 under the unusual assumption that I, normally the imaginary unit, is equal to the natural logarithm of 2. Substituting the assumption, he replaces I with ln2 in the exponential form. So e to the ix becomes e to the ln2 times x. Simplifying the exponential when using the properties of exponents, this simplifies to e to the ln2 times x equals e to the ln2. Since e to the ln2 equals 2, this implies that x equals 1. Magnitude check. Now looking at the magnitude of the original expression 1/2 times e to the ix, the magnitude of e to the ix under this assumption is 2. Multiplying by 1/2 gives 1, which matches the right-hand side of the original equation. Final substitution: substituting back, he writes 1/2 times 2 equals 1, which confirms the calculation. So, under this special assumption that I equals ln2, the equation seems to work numerically, even though this is outside standard complex analysis. This is part of the author's method for exploring logarithms and magnitudes in the context of negative logarithms and the zeta function. The author is analyzing the equation 1/2 times e to the ix equals 1 under the unusual assumption that I equals the natural logarithm of 2. Simplification under the assumption when substituting I as ln2, the equation simplifies neatly to 1 equals 1. This shows that within this assumption, the equation is consistent. Importantly, it does not imply something nonsensical like 1 equals 2. It just confirms that the equation works under this framework. Correct interpretation of the equation when the equation should not be misread as implying 1 equals 2. Instead, the proper way to analyze it is through the exponential form of complex numbers e to the ix equals r times the sum of a sin x and I sin x. Using derivatives to understand the behavior when taking derivatives of both sides and then separating into real and imaginary parts shows that the magnitude r is constant and the argument x behaves linearly up to some constant. Assigning values if we assign the magnitude r as 1/2 and assume I equals ln2, then the product r times e to the ln2 equals 1. The initial value x equals 1 then gives I equals ln2, fitting consistently with the assumptions. Geometric interpretation fit in a higher dimensional, four-dimensional perspective, the imaginary number I acts as a constant scale factor, helping to maintain the rotational symmetry of a complex plane and the cycles described earlier. So the key idea is that under this very specific, non-standard assumption, the equation holds consistently and the magnitude and argument behave as expected without leading to any contradictions like 1 equals 2. The author is extending the discussion of the imaginary number I and its logarithmic interpretation using quaternions, which are a generalization of complex numbers into 4 dimensions. Quaternions and exponentials. The text recalls a familiar rule from exponentials. When you multiply e to the a plus b, it equals e to the a times e to the b. But this only works if a and b commute, meaning their order doesn't matter. For quaternions, which can involve rotations in multiple dimensions, a and b might not commute. In that case, the exponential of a sum becomes more complicated, involving the sum of a b, their product, and higher-order combinations, plus vector cross products. Parallel vectors simplify things when the two components of the quaternion are almost parallel, their product becomes negligible. So the exponential behaves almost like in the standard commuting case. This allows the algebra of rotations to approximate the simpler vector algebra we are familiar with. Unit disks and cycles. For earlier, the author described 3 parallel unit disks in the complex plane. These appear parallel in this higher dimensional view, which simplifies operations. Using this setup, complex exponentials and logarithms can be handled almost like real numbers. Completing the cycle with quaternions, just like in Euler's formula where e to the I plus 1 equals 0. the author proposes applying a similar principle to quaternions. This allows quaternion exponentials to be interpreted as real numbers along a consistent cycle, maintaining the structure needed for the analysis of the imaginary unit and related logarithms. In short, quaternions are used here to justify treating the imaginary unit I and complex exponentials in a way that mimics real numbers by using their rotational and multidimensional properties, which simplifies the algebra and preserves the cyclic relationships the author is exploring. The author is extending the earlier discussion of complex exponentials, logarithms, and quaternions to show how the formula z equals 1/2 times e to the ix equals 1 can be interpreted for generalized complex numbers. Starting with an infinite series, then they consider an infinite product of exponentials e to the q1, e to the q2, e to the q3, and so on. This product can be expressed as the exponential of the sum of all the q's qn e to the q1 plus q2 plus q3 plus connection to logarithms when using the previous assumption that I equals the natural logarithm of 2. This sum of q's simplifies to 2 times ln2. Then the exponential of that e to 2 ln2 can be broken down as e to ln2 times e to ln2, which equals 2 times 1/2, giving a result of 1. This demonstrates the correctness of the general formula in this generalized setting. Quaternions in the series within each term in the infinite sum can be associated with quaternion components I, j, k, plus scalar terms. When summing these components, using the specific zeta values in the series, the imaginary parts cancel out to 0, leaving only a real component of 2 times ln2 cycles. In zeta series, when the author points out a cycle of 3 and 4 infinite series of zeta values, which manifests as 2 alternating infinite zeta series. This pattern naturally aligns with the previous calculation, reinforcing the result that 1/2 times e to ln2 equals 1 in this extended, generalized framework. In essence, the passage shows that by considering infinite series quaternion decomposition and the earlier assumption about I, the generalized complex exponential behaves consistently and produces the expected value, maintaining the underlying cyclic structure of zeta values. The author is summarizing and expanding on the earlier discussion about the equation z equals 1/2 times e to the ix equals 1, showing why it works and why it does not lead to nonsensical results like 1 equals 2. Complex logarithm as a multivalued function. They point out that I times x equals the logarithm of cos plus I sin is a multivalued function. This happens for 2 main reasons. First, because of the infinite rotations around the unit circle. If you rotate by full circles repeatedly, the exponential repeats. Second, because in higher dimensional number systems, like quaternions discovered by Hamilton, there are multiple real solutions for I. These higher dimensional systems, including extensions like Clifford algebra or vector algebra in 3 dimensions, connect to 4-dimensional structures that appear in algebraic cycles studied by mathematicians like Hodge, Tate, and Weil. These structures are not fully proven algebraically, but numerically. Evidence from zeta function calculations suggests they exist, completing the algebraic cycles. When the author talks about the cycle 1 plus I minus 1 minus I equals 0, they explain that completing this cycle actually completes 2 semicircles, corresponding to the classical exponential identity e to I pi plus 1 equals 0. This shows that the algebra is consistent, and it is wrong to interpret this as meaning 1 equals 2. Instead, we should interpret it in a consistent way, like 1 equals 1 or 2 equals 2. Pi and complex logarithms. Finally, the author notes that pi is deeply connected to e and to the circle, but asks whether it can also serve as a base for complex logarithms. This hints at the interplay between circular geometry, exponentials, and logarithms in complex and higher dimensional algebra. In short form, the passage explains why the formula is valid, how multivaluedness arises from both rotations and higher dimensional numbers, and emphasizes that algebraic consistency is preserved, so we never get paradoxes like 1 equals 2. The author is exploring how logarithms, even ones that are not commonly used, can be applied to complex logarithms and related infinite series. Using series to express logarithms, they start with an expression involving the natural logarithm of 2 raised to the 4th power. This is written as a sum of fractions such as 1/2, 1/3, 1/4, and so on, sometimes combined with alternating signs or multiplied together. The goal is to rewrite these sums in a way that connects to trigonometric or hyperbolic functions, connecting to sine and cosine. After some manipulation, the sum is expressed as a combination of sine of I plus cosine of I, where I is the imaginary unit. This is a bridge from the original infinite series to functions that are easier to handle in complex analysis. Introducing the substitution for simplification, they set this combination, sine of I plus cosine of I, as a single variable. Then, using the fact that natural logarithms can be represented through exponentials, they rewrite the original equation involving ln2 to get an expression like e to the ln2 times 4 equals I times e. And finally, this is simplified to I times e equals 1. Hyperbolic functions and exponentials. Finally, the author begins to express hyperbolic cosine of ix in terms of exponentials, which is a standard technique in complex analysis. The hyperbolic functions, like cosine hyperbolic, are connected directly to exponential functions, making it easier to manipulate them in proofs or further calculations. In short, from this passage shows how seemingly complicated sums and logarithms can be translated into exponential, trigonometric, or hyperbolic forms, eventually leading to neat expressions like I times e equals 1. It sets up the tools for using complex and hyperbolic functions in the study of the zeta function and related lemmas. In this section, the author is connecting complex exponentials to hyperbolic functions to better understand the behavior of logarithms and exponentials in the complex plane. Hyperbolic sine with imaginary argument. They start with the hyperbolic sine of I times x. By definition, hyperbolic sine involves a difference of exponentials divided by 2 times I. When we substitute e to the ix and e to the negative ix into this formula and use the standard Euler relations, where e to the ix is cosine of x plus I times sine of x, and e to the negative ix is cosine of x minus I times sine of x, the calculation simplifies neatly, simplifying sin Roman 9 and cos Roman 9. Hyperbolic cosine of ix becomes cosine of x. Hyperbolic sine of ix becomes I times sine of x. So, just like Euler's formula for real exponentials, we can write the complex exponential e to the ix as the sum of hyperbolic cosine and I times hyperbolic sine for e to the ix equals cos of ix plus I sin of ix, which reduces back to cosine x plus I sin x. Connecting back to previous results, the author then expresses e to the ix in terms of sums and averages of exponentials, showing that when combined properly, this leads to a simple expression like 1/2 times 2 times e to the ix equals 1. This is part of the broader framework in the text where complex exponentials, hyperbolic functions, and logarithms are connected to understand multi-valued behaviors and algebraic cycles. In short, the key takeaway is that hyperbolic functions with imaginary arguments can reproduce the usual sine and cosine relationships, and this allows complex exponentials to be expressed neatly in terms of hyperbolic cosine and sine, forming a bridge between real, complex, and hyperbolic analysis. In this section, the author is exploring the logarithm of 1 and how this concept extends into complex numbers and quaternions. The usual logarithm. Normally, the natural logarithm of a number is defined only for positive real numbers. For example, the logarithm of 2 tells us the power we need to raise e to get 2. Extending to complex numbers, to handle negative numbers or complex numbers, we use the complex logarithm. For any complex number z, the complex logarithm is written as the logarithm of the magnitude of z plus I times the argument, the angle of z. The magnitude is just the distance of the point from the origin, and the argument is the angle it makes with the positive real axis. Logarithm of 1 in the complex sense, take z equals 1. Its magnitude is 1 because it sits 1 unit away from the origin and its argument is 0, or you can add any multiple of a full rotation, 2 pi for generality. So, using the complex logarithm formula, the logarithm of 1 is I times the argument, because the argument can be 0. This gives ln of 1 equals 1 under the assumptions or definitions the author is exploring. In short, the author is justifying that in the context of complex numbers and eventually quaternions, taking the logarithm of 1 can be extended meaningfully, linking the magnitude and angle to define it in a way consistent with the algebraic framework being developed. In this part, the author is discussing the logarithm of 1 in the context of complex numbers and non-standard assumptions. Standard result. Normally, the complex logarithm of 1 is defined as I times the argument of 1, and since the argument is 0, the principal value is I times 0, which is 0. So, traditionally, ln of 1 is 0. Alternative framework. The author is exploring a different theoretical framework where the logarithm might be considered differently. In some unconventional conventions, or with special numerical bases, one might define the logarithm in such a way that ln of 1 could be considered equal to 1. Key idea. This does not contradict standard mathematics, it simply uses a different branch or convention of the logarithm function. By making an assumption like I equals the natural logarithm of 2, the author shows that under this special framework, the evaluation of ln of 1 can be handled consistently with the claim ln of 1 equals 1. In short, while normally ln of 1 is 0, under specific assumptions and alternative conventions, the author shows it is possible to treat ln of 1 as equal to 1, and this is used to support further analysis in the context of negative logarithms and complex/quaternion algebra. The author is continuing the discussion of the logarithm of 1, now explicitly using the formula for the complex logarithm. Complex logarithm formula. For any complex number z, the logarithm can be written as the natural logarithm of its magnitude plus I times its argument. So for z equals 1, the magnitude is 1 and the argument is 0. Normally, this would give ln of 1 equals 0 plus I times 0, which is just 0, introducing the assumption I equals ln of 2. The author then assumes that the imaginary unit I can be replaced with the natural logarithm of 2. Substituting this, the logarithm of 1 becomes ln of 1 equals I, which under this assumption is ln of 2. So now, ln of 1 is treated as ln of 2 under this framework. Connection to Riemann constants and quaternions. Next, the author invokes a relationship involving the inverse of the logarithm and the Riemann constant at 0, which is 1/2, to rewrite ln of 1 in a way that evaluates to 1. Essentially, ln of 1 is expressed as 1/2 times e to the ln of 2, which equals 1. Lemma 8. This shows that assuming I equals ln of 2 provides a consistent way to handle negative logarithms and the ambiguities in defining the principal value of the complex logarithm. The author notes that to fully justify this, we need to use quaternions, which allow extensions of complex numbers into higher dimensions. In short, when by reinterpreting I as ln of 2 and using connections to Riemann constants and quaternions, the logarithm of 1 can be handled in a way that resolves certain indeterminacies, supporting further constructions in the theory. The author is exploring logarithms of 1 and related numbers in the context of quaternions, which are numbers extended into higher dimensions beyond the usual real and complex numbers, visualizing the principal logarithm in quaternions. Normally, the logarithm of 1 is 0, but here the idea is to treat the logarithm not as a simple number or a product of two imaginary units, but as a set of quaternion components. For example, you could think of it as the logarithm of a combination like I squared, j squared, k squared, and their products. Vector sum analogy. When you take the logarithms of these quaternion components and add them as vectors, you want the sum of 3 equal vectors to equal 0. Geometrically, in 3 dimensions, this happens when each vector makes an angle of 120 degrees with the others. In 4 dimensions, this corresponds to a 60-degree angle. This shows that numbers, while simple in everyday use, have hidden multi-dimensional structures in quaternion space. Generalizing logarithms using cycles. Using this quaternion perspective and limiting the number of cycles, cyclic limits, the author generalizes the logarithm values. The logarithm of 1 becomes 1 after applying the scaling factor. The logarithm of 1/2 becomes 1/2 after scaling. The logarithm of 1/3 becomes 1/3 after scaling. Essentially, the logarithm operation is being extended to a multidimensional cyclic framework where familiar numbers are connected to deeper structures in 3 or 4 dimensions. In short, by thinking of logarithms in quaternion space and using vector sums with specific angles, The author resolves ambiguities in the logarithm of 1 and generalizes logarithms for fractions, revealing hidden multidimensional patterns behind simple numbers. The author is continuing the discussion on negative logarithms and how Euler's ideas about them hold up, especially when extended into complex and quaternion contexts. General pattern for logarithms. The text shows that the pattern for logarithms, including fractions like 1/2, 1/3, and so on, continues indefinitely, even toward negative infinity. This aligns with Euler's historical observations on negative logarithms, quaternions, and closure of logarithms. In the complex sense, the logarithm operation can be closed under quaternions, meaning it works consistently even for negative numbers or more complicated multidimensional numbers. Quaternions allow these operations to be defined in higher dimensional algebra. Examples of logarithms using quaternions. The author gives explicit calculations. For the natural logarithm of -1, they start with a quaternion solution. Using the formula that involves I and logarithms, they get approximate values. Similarly, logarithms of fractions like 1/2, 1/3, and whole numbers like 3 are calculated by combining the quaternion-based logarithm of I squared with the usual logarithm. The results are specific numeric approximations, showing how the quaternion approach produces consistent values. Transition to the Riemann hypothesis. Having established this framework for negative and complex logarithms, the author is now ready to apply these tools toward a proof of the Riemann hypothesis. In short, by using quaternions, the author extends the logarithm operation to handle negative numbers and fractions in a consistent way, confirming Euler's ideas and setting up the mathematical machinery needed to approach the Riemann hypothesis. The author is beginning the actual proof of the Riemann hypothesis using Euler's product formula for the zeta function. Let's break it down step by step. Euler's product form of the zeta function. The zeta function, which normally sums over all natural numbers, can also be expressed as an infinite product over prime numbers. In this form, each prime generates a factor in the product, and these factors can be written using Euler's exponential form for complex numbers. Structure of each factor. Each factor looks like 1 plus r times e to the I, plus r squared times e to the 2i, plus r cubed times e to the 3i, and so on. This is an infinite geometric type series where r is a magnitude and the exponentials encode rotations on the unit circle in the complex plane. When does a factor vanish? A factor becomes 0 when the sum of the series excluding the initial 1 equals 1 in exponential form. In other words, the infinite sum of r squared, r cubed, etc. multiplied by their complex rotations equals 1. Relating to the unit circle, by comparing both sides of the equation on the unit circle, the author essentially translates the problem into a question about points on the circle. The series of exponents 1 plus 2 plus 3, and so on relates to the geometric progression of r squared, r cubed, etc. Goal. The next step is to solve for r and the exponentials so that the equality holds. This is the start of the author's strategy for linking the Euler product form to the distribution of zeros of the zeta function, which is at the heart of the Riemann hypothesis. In simple terms, the author is using the fact that the zeta function can be expressed as a product over primes, converting it into a problem about sums of complex exponentials on the unit circle, and setting up equations whose solutions will identify the critical zeros. The author is continuing the proof of the Riemann hypothesis using the Euler product form and geometric series ideas. Let's go step by step. Infinite series of natural numbers and geometric series. The author first writes the series of natural numbers 1 plus 2 plus 3 plus 4, and so on, and connects it to a geometric series of the form r plus r squared plus r cubed, and so on. Using the standard formula for an infinite geometric series, we know that r plus r squared plus r cubed and so on equals r divided by 1 minus r. Setting this equal to 1 gives the equation to solve for r. Solving for r. From the equation, the solution for r turns out to be 1/2. This r represents the magnitude factor in the complex exponential series, determining the real part of the zeros. Next, the author looks at the real part of the non-trivial zeros of the zeta function. Using the relationship between the magnitude r and the angle in the unit circle, the cosine of the angle times r equals 1/2. This leads to the conclusion that the principal value of the real part is 1/2. Conclusion. Because the real part of every non-trivial zero comes out to be 1/2, this satisfies the condition stated in the Riemann hypothesis, which claims that all non-trivial zeros of the zeta function lie on the critical line where the real part is 1/2. Alternative viewpoint. The author suggests that one could also start from the trigonometric form of complex numbers, sum algebraically, and then return to the exponential form. This is essentially using different but equivalent representations of complex numbers to reach the same conclusion. In simple terms, by translating the Euler product into a geometric series and solving for the magnitude, the author shows that the real part of all non-trivial zeros of the zeta function is 1/2, which is exactly what the Riemann hypothesis predicts. The author is looking at a series of complex numbers in exponential form. Each term is a magnitude r to a power times the exponential of I times an integer multiple of an angle. This is just a fancy way of writing numbers in the complex plane as points on a circle. Breaking down each term, like r times e to the I angle, can be rewritten in trigonometric form as r times cosine plus I times r times sine. So r e to the I equals r cos plus I r sin. Similarly, r squared e to the 2I angle equals r squared cos 2 plus I r squared sin 2, and so on. Summing terms as vectors, when we add all these complex numbers together, we can think of it as adding their x components, the cosine parts, and their y components, the sine parts, separately. So the sum becomes a new complex number, whose x-coordinate is the sum of all the cosines times their respective magnitudes, and y-coordinate is the sum of all the sines times their magnitudes. Modulus and argument of the sum, the modulus, or magnitude, of this resulting complex number is like the length of the vector from the origin to the tip of the sum vector. The argument, or angle, is the direction of this vector from the origin. In other words, after summing all the individual vectors, we get a single vector whose length and angle capture the combined effect of all terms in the series. Geometric interpretation. You can visualize each term as a point on the unit circle. Adding them is the same as stacking these vectors tip to tail, even though each individual vector has a magnitude of 1 or r squared, etc. The final vector will usually have a smaller or larger magnitude depending on how the individual vectors point relative to each other. The final angle is the direction of this combined vector. Summary: the sum of the series is not just a number, it's a vector sum in the complex plane. Its modulus tells you how long the resulting vector is, and its argument tells you where it points. This method allows us to connect the geometric picture on the unit circle with the algebraic series of complex numbers. In essence, the author is translating the series of complex exponentials into a vector addition problem in the plane to better understand the sum and its properties. The author is addressing some subtleties when working with complex numbers in exponential form, particularly in the context of the zeta function and primes. Absurdity of 0 equals 1. The text points out that directly writing something like r times 1 minus r can misleadingly look like 0 equals 1. To avoid this mistake, we need to use the complex conjugate of the denominator before simplifying. In other words, we multiply numerator and denominator by the conjugate to get a valid expression. Doing this carefully shows that r simplifies correctly to a value on the unit circle, which is where complex numbers of magnitude 1 lie. Interpretation of r equals 1. When we say r equals 1, it should be understood as an exponential relationship on the unit circle. This expresses that raising a number to a certain power can give 1, which is similar to saying that logarithms of 1 are 0 in real numbers. The author emphasizes that in this framework, there is no t-unit circle satisfying 3.3 to 1 equals 1. Only the usual unit or d-unit circle matters. Connecting complex logarithms to real logarithms, proving something like log base 2 of 1/2 equals 1 in a complex sense is essentially equivalent to the simpler real statement log of 1 equals 0. In other words, the complex framework generalizes the familiar real number logarithm properties. Moreover, primes other than 2 also satisfy similar relationships when expressed using complex exponentials. Addressing potential objections. Some might argue that every exponential in the form e to the I something must be prime, and that generalizing may not make sense. The author clarifies that no such assumption is made. The method works because we are applying the exponential form to products over primes, which automatically accounts for composite numbers as products of primes. This aligns with Riemann's original approach in using the prime product form of the zeta function, Euler's alternate product form. Finally, the author introduces an alternate version of Euler's product form for the zeta function using exponential form. This expresses the sum over natural numbers as a product over primes, with each prime term written in terms of these complex exponentials. This alternate form reinforces the connection between complex exponentials and the structure of primes, which is central to understanding the zeros of the zeta function. In short, this passage carefully handles complex exponentials, unit circle interpretation, and primes to ensure the formulas make sense, avoid contradictions like 0 equals 1, and extend the properties of real logarithms to the complex domain in the context of the zeta function. The author is continuing the proof of the Riemann hypothesis using the Euler product form of the zeta function in exponential form. The main idea here is manipulating each factor in the product to understand the zeros. Multiplying numerator and denominator, we start with a term of the form ρ divided by ρ minus 1. To simplify, we multiply both the numerator and denominator by ρ plus 1. This is a standard algebraic technique to remove denominators and make the expressions easier to analyze. Setting factors to 0. After this multiplication, a factor in the product looks like ρ times ρ plus 1 divided by ρ minus 1 times ρ plus 1. The text explains that this factor will equal 0 if the numerator equals 0, meaning ρ times ρ plus 1 equals 0. Breaking down the equation, we expand this and examine the powers. ρ times ρ is ρ squared. The product equals 0 if ρ squared minus ρ or other equivalent forms equals 0. Solving for r. From this, the author solves for the magnitude r of the complex number on the unit circle. Step by step, they reduce the equation and find that r equals 1. This makes sense geometrically because points representing complex numbers of magnitude 1 lie on the unit circle, which is central in complex analysis and in understanding the zeta function's zeros. In simple terms, this step shows that by carefully manipulating the exponential factors and setting them to 0, we find that the magnitude of these complex numbers must be 1, confirming they lie on the unit circle. This is an important piece in connecting the zeta function to the location of its non-trivial zeros, which is what the Riemann hypothesis is about. The text is now addressing the real part of the non-trivial zeros of the Riemann zeta function and provides a pathway to the proof of the Riemann hypothesis. Finding the real part, the author starts by considering the magnitude of a complex number on the unit circle, denoted by r, and its angle. Using trigonometry, they take the real part of this complex number, which is calculated as the magnitude times the cosine of the angle. In the example given, this comes out to 1/2. This shows that the principal value, or the real part of the non-trivial zeros, is exactly 1/2. This directly corresponds to the statement of the Riemann hypothesis, which says all non-trivial zeros lie on the line in the complex plane, where the real part is 1/2. Special case of the unit cycle. The author then walks through a series of manipulations with the complex exponential, showing that by repeatedly applying powers and combinations of the exponential, it cycles back to itself or to 1. This illustrates a unit cycle property of the complex exponential and reinforces the idea that the values involved remain on the unit circle. Essentially, this is a way to verify the internal consistency of the earlier calculation. Alternate functional equation. Next, the text moves toward an exhaustive approach using the Riemann functional equation. By multiplying both sides by a shifted argument, the author is setting up the framework to analyze the symmetry of the zeta function. This functional equation relates values of the zeta function at s and 1 minus s, and multiplying both sides is a standard step to explore zeros symmetrically across the critical line. In simple terms, this section ties together trigonometric reasoning on the unit circle, the complex exponential's cyclical behavior, and the functional symmetry of the zeta function to argue that the real parts of non-trivial zeros must be 1/2, which is exactly what the Riemann hypothesis asserts. This section continues the effort to prove the Riemann hypothesis using the functional equation of the zeta function. Manipulating the functional equation, the author begins by combining two shifted forms of the zeta function, multiplying them together to produce a new expression. This allows them to express the zeta function in a slightly different form that involves the sine function and a gamma function term. The purpose here is to make the behavior of the zeta function more transparent, particularly near its critical line, limits and normalization. They examine the behavior as certain variables approach 1 or 0, effectively taking limits. This shows that in these limiting cases, the expression simplifies nicely, giving results like 1/2. These calculations help clarify the structure of the zeros and poles of the function, poles and the gamma function. The text points out that the pole of the zeta function of the real part equal to 1 comes from the pole of the gamma function in the functional equation. In other words, the divergence of the zeta function at that point is inherited from the gamma function, not an independent feature. Critical strip and delta function. Inside the critical strip, where the real part of S is between 0 and 1, the author suggests introducing a delta function related to factorials to control the behavior of the gamma function. This allows them to remove or neutralize the poles, effectively smoothing out the function while preserving its key properties. Holomorphic property. The zeta function is holomorphic, meaning it's complex differentiable everywhere in the critical strip except at its poles. Because of this property, stretching or compressing the function, for example, via the delta function adjustment doesn't break this differentiability. This is crucial for maintaining the validity of further manipulations and for the proof strategy. In simple terms, this passage is about carefully adjusting the zeta function using its functional equation, sine and gamma function terms, and the delta function to control its poles while keeping it smooth and differentiable. This sets up the groundwork for analyzing zeros on the critical line. This section focuses on rewriting the functional equation of the zeta function in several equivalent ways to make its properties more transparent. Functional equation and harmonic conjugates. The author starts by expressing the zeta function using its functional equation in terms of a harmonic conjugate function. This form involves the sine function and shifted versions of the zeta function. The idea is to highlight symmetry properties and relationships between the zeta function at different points. Gamma and pi functions. The functional equation is then rewritten in terms of the gamma function, which generalizes factorials to complex numbers. Later, it is rewritten using the pi function, which is closely related to the gamma function. These rewritings allow the author to manipulate the zeta function more flexibly in complex analysis, particularly when considering its zeros and poles. Evaluating at S equals 1. By substituting 1 into the equation, they check the behavior at a key point, confirming that the functional equation holds and the expressions simplify in a consistent way. This also demonstrates that the zeta function can be extended to a function defined on the entire complex plane except for known singularities, which is essential for further analysis. Entire functions and Liouville's theorem. Finally, the author points out that once the zeta function is defined everywhere on the complex plane excluding singularities, it becomes an entire function. In complex analysis, Liouville's theorem says that any bounded entire function must be constant. This is a key concept because it restricts the types of behavior entire functions can have, providing constraints that are useful in proving results about the zeta function, including its zeros. In simple terms, this passage shows how the zeta function can be rewritten using sine, gamma, and pi functions extended across the complex plane and analyzed with powerful tools like Liouville's theorem to understand its global behavior. This section explains why the non-trivial zeros of the zeta function lie on the critical line with real part 1/2, using ideas from complex analysis. Zeta as an entire function. The zeta function, when extended across the complex plane, becomes an entire function, which means it is complex differentiable everywhere. Being entire and bounded, the author argues that the zeta function behaves like a constant function with respect to certain maximum and minimum principles. Maximum modulus principle. In complex analysis, the maximum modulus principle says that a non-constant holomorphic function reaches its maximum absolute value on the boundary of a domain, not inside. Here, the domain is a unit circle or a double unit circle, and the maximum absolute value of the zeta function is denoted as approximately 2 to the sixth power. This principle helps us understand how the function behaves on the boundary versus inside. Gauss's mean value theorem. This theorem states that for a function bounded in some neighborhood, the average value occurs at the center of that neighborhood. Applying it to the zeta function, the author identifies that the mean modulus, or average absolute value, occurs at the center of the unit circle, which is around 1/2. Inverse and minimum modulus principles. The minimum modulus principle says that a holomorphic function with no zeros reaches its minimum on the boundary. However, the zeta function has many zeros, so its minimum modulus does not occur on the boundary, but inside the domain. In this analysis, the half-unit circle is identified as the locus where the minimum modulus occurs, corresponding to the zeros of the zeta function. Conclusion about zeros. Combining these principles, the author argues that the zeros of the zeta function lie on the half-unit circle, which translates to the critical line where the real part of S is 1/2. This aligns perfectly with Riemann's original hypothesis. Final substitution. To finalize, the author shows how plugging S equal to 1/2 into the functional equation confirms the location of zeros mathematically. In simple terms, this passage uses the behavior of entire holomorphic functions, maximum and minimum modulus principles, and averaging properties to justify why all non-trivial zeros of the zeta function lie on the line where the real part is 1/2, exactly what Riemann predicted. This subsection reviews the final steps of the proof of the Riemann hypothesis, connecting the earlier ideas about negative logarithms, quaternions, and complex numbers to the actual location of the zeta function's zeros. Critical relationship. The key assumption is that the imaginary unit I is equal to the natural logarithm of 2. This unusual assumption lets the author define negative logarithms in a way that fits the behavior of the zeta function in the complex plane. Negative logarithms table. Using this relationship, the logarithm of 1 is interpreted not in the standard sense of 0, but in a generalized form ln1 equals 2 times the logarithm of the logarithm of 2. This may sound abstract, but it is part of the framework the author uses to extend logarithms into higher dimensions and quaternionic space. Connection to zeros of zeta function. By applying this interpretation consistently, the negative logarithms help explain the pattern of zeros of the Riemann zeta function. Essentially, it provides a way to connect the complex logarithm behavior to the critical line, where the real part of the zeros is 1/2. Summary. In short, this review highlights that through the generalized treatment of logarithms and using the critical formula I equals ln2, the distribution of zeros on the critical line can be systematically justified. A table of negative logarithms is a tool to visualize and check this correspondence. This section ties together the earlier quaternion and complex logarithm analysis with the final placement of the zeros, giving a unified view of the argument. This section focuses on a key part of the proof of the Riemann hypothesis by exploring a special, non-standard idea about the imaginary unit I. Key relationship. The author proposes an unusual but useful definition for ln I equals the natural logarithm of 2. This is not how we normally define I, but in this framework, it helps extend logarithms into complex and higher dimensional spaces. Implication for logarithms. With this definition, the logarithm of 1 can be rewritten in terms of I. Step by step, ln of 1 equals ln of I squared, which equals 2 times ln of I, and finally equals 2 times the natural logarithm of ln of 2. This establishes a new structure for logarithms in the complex setting and gives a way to handle negative or unusual logarithmic values. Constructing a table. Using this relationship, the author constructs a table of negative logarithms. This table calculates values of the logarithm for different inputs, now interpreted using the I equals ln2 framework. The goal is to see patterns and connections that reveal how the zeros of the Riemann zeta function are distributed, particularly along the critical line, where the real part is 1/2. In short, this part sets up a mathematical lens. By redefining I in terms of ln2, we can reinterpret logarithms and systematically explore the behavior of a zeta function.